So we're still gonna talk about random walks and spectral expansion because these all factor into this definition, but this definition has also a lot to do with linear algebra over maybe finite fields or even other groups of coefficients, and it is somewhat different and maybe a little bit more mysterious still. We still don't quite understand it as well as we do the spectral type of expansion. I wanted to talk about it and talk about local testability relating to Siki's talk from last week and maybe to other talks we've heard through the semester. So let me start by basically I want to do some background and setup. So basically just talk about the spectral expansion. Graphs. So if I have today, all my graphs will be deregular. And so if I look at the adjacency matrix, where I put a 1 between a u and v if there's an edge and 0 otherwise, instead of putting a 1, I'm going to put a 1 over d so that the matrix describes the random walk on the graph, namely you start from a vertex, and then with equal probability you go to one of the neighbors, and so on. And then a graph is called the lambda expander. And lambda is going to be something strictly smaller than 1. If this normalized adjacency matrix, the second largest eigenvalue is at most lambda. So if let me write, if inner product of F with, we call this adjacency matrix M. This is the normalized adjacency matrix. And if I have some function on the vertices, so F is some real valued function on the vertices, then the inner product between F and MF okay, maybe I should also say, when I talk about inner product here, it won't matter, but I like to think of inner product as average rather than sum. So that's going to be 1 over the cardinality of the vertex set, and then summation over V, F of V. Here, if it was some G, here it's going to be MF at V. This is my definition of the inner product. So it's really just expectation over the vertices. And this is convenient because sometimes you have other kind of weighted distribution over your vertex set, and then you just take average with respect to these weights. For today, it will always be just a uniform expectation. So a graph is going to be a lambda expander if this is most. So this is that. This is at most lambda times the the norm of. Okay, and for a normalized adjacency matrix, lambda is always between -1 and 1. The top eigenvalue is always going to be 1, and the eigenfunction is the all ones function. And I also already want to kind of state one of the lemmas that makes spectral expansion very useful. This is the Alon-Chang lemma. And it says that.
Don't you have to take out the top eigenvector? It should be F without no to the right F. That's
thank you. Yeah.
Why does it make much sense?
Yeah, you're right. Expectation of F is 0.
Yes.
Thank you. Okay, so often when we talk about spectral expander, we say, what is a combinatorial interpretation of this? We have the expander mixing lemma, but another form of the expander mixing lemma is the Alon-Chang lemma, and it says,
Just, I'm sorry.
Yeah.
Are you looking at a one-sided or a two-sided expander? Do you need absolute values?
right, so it depends. This definition is one-sided.
One-sided, so one-sided is going to be, all right.
Yeah, I'm not, yeah, for now, I'm talking about one side.
Okay.
Sometimes we want to say that in absolute value, and then this gives me the two side. Okay, so the Alon, let me see if I'm missing something. So if it says the following, if given a lambda expander, suppose I have a set T, a subset of the vertices, okay, such that the average degree of a vertex in T, when I ask how many neighbors are in T, is at least delta with average degree at least delta times D. So here, so it's a D regular. Okay, so the picture here is, here is my graph G, and I have some set of vertices T. And I know that if I have a vertex inside T, some of the neighbors go outside of T, but at least delta fraction of the neighbors go inside T. And that's not for every vertex, but on average. So maybe some vertices in T, all of their neighbors go out, but on average, a lot of the edges stay inside. Okay, so T is a set of vertices that kind of, if I think of a random walk starting from T, then with probability delta, I stay inside of T. So you can think of it as like the staying probability of this set. Okay, so if in an expander, if you have a set so that the random walk kind of stays inside the set with probability delta, then T must be large. Then T must be at least delta minus lambda times V. Okay, that's the conclusion. So if delta is smaller than lambda, this means, this says nothing. I don't know anything about the set. But if delta is, actually, am I missing another delta here? Say. But if delta is bigger than lambda, you cannot have a set whose staying probability is bigger than delta without this set being a linear fraction of the graph. There's no small set that you kind of get stuck inside the set. So that's one way to understand what expansion means. And let me do a proof of this lemma just to show you that it's very simple. Okay, so fix.
So it's not just one side of the Jigger inequality, or
It's just one of the ways to think about spectral expansion. It's a one-line proof. Okay, so how do we prove it? So I'm given this set T, and I'm thinking of the function. Let me write it as f. F is the function that is 1 on T and 0 everywhere else. And let me also write P to be the expectation of F. So that's like the fraction of vertices inside T. We want to prove that P is large. Okay, so I write F as P times the all one function plus I call it F perp. So I just define F perp to be F minus P. Okay, the reason I do that is because this guy has expectation 0. It's just a spectral decomposition. And then I look at this expression, FMF. So on one hand, I can expand it. I can plug in this decomposition and see what I get. And on the other hand, I have some interpretation of what this is, right? So what is this? it's, if I look up there, it's the expectation when I take a uniformly random vertex. F of B tells me if I'm in the set or not, and MF of B tells me what's the probability of staying inside of it. So this is exactly going to be, well, it's going to be at least P times delta by our assumption. So probability P, I'm starting inside an element of my set, and with probability delta, when I go to a random neighbor, I stay inside the set. Okay, so this is at least P times delta, and on the other hand, I get, just from plugging this in, I get, I guess, P times 1 plus F perp, P times 1, and here I have M P times 1 plus F perp. So, okay, so M is the adjacency operator of the graph. So, okay, M times 1 is 1, so P just comes out. And M times F perp, this is where I apply my expansion, and I know that it's mostly lambda. So I have here P squared plus F perp, M F perp, which is at most P squared plus lambda, and then I have the norm F perp, which is at most the norm of F. No, I should have, I guess, 1 minus P here. Sorry, just 1 minute.
Also, that's actually the invisible part of the board.
Oh, am I in the part? Oh, good. Okay, so if I make a mistake, no worries.
Because I can't see it anyways.
Okay, so I have here P squared plus lambda P. And what do I get from this? Should give me something. I get here P times delta minus lambda is at most P squared, so P must be at least delta times lambda. Do you see that? And I got this inequality, P times delta is at most P squared plus lambda P, so this gives me exactly what I want. So it's not so important. The point was that it was like a one longish line proof that just follows from expanding F into the constant component and the orthogonal component and using the spectral bound. And this is kind of what we're going to use later. We're going to use the fact that a graph is an expander means that no random walk can be stuck in a small set. If you want to prove that your set is large, you prove that there is a random walk that kind of stays inside the set with large probability. And this means that your entire set must be. So let's see an application of this. I do it here. So application. Expander codes. I start with some graph which is deregular. And lambda expander. And I also have some code which is on a subspace of d bits. And I assume that for every code word that is not a zero code word, the number of non-zeros in this code word is at least delta times d. So this means that this collection of strings, every non-zero string has a number of 1. And now we define the code C, which depends on G and on C not, to just be, okay, so let me just draw a picture. So here is my graph G. And my code is going to be functions on the edges that give zeros and ones to different edges. And the requirement will be that around every vertex, the sequence of bits that you see belongs to the small code. So here in this example, the code has 4 bits. And around every vertex, I see some sequence of bits that belongs to the small code. So let me define it. It's the set of functions from the edges to 0, 1, 2, I don't know. Such that for every vertex in the graph, if I look at the function restricted to the edges, let me use this notation, it's the restriction of the function to the edges touching this vertex. And this notation is a bit ambiguous, but there's implicitly an assumption that there is some fixed ordering of the edges around every vertex. I want that this belongs to the small code.
But this ordering can be arbitrary or has to be compatible between different vertices?
It's arbitrary.
Okay.
It's a very good question. Later it will have to be compatible. Right now it's arbitrary. So I need to really say, fix a graph, fix an ordering, and fix a code. And then this is the. Okay, so I made this definition. And if you want to think about it, really what I defined here is a kind of parity check matrix for the code where I have a kind of rectangular matrix where I have a column for every edge. So my code word is going to be some vector here whose coordinates correspond to the edges. And a string will be in my code if it's in the kernel of this matrix. So what is this matrix? Well, for every vertex, I don't only have one row, I actually have a bunch of rows. How many of them? As many as you need to do parity checks for C0. And so imagine, for example, that the neighbors of V are the first D vertices here, then really what I put here is the parity check matrix of C0. And then if this is for V1, and then if for V2, I have another bunch of rows, and maybe I put here the parity check matrix again along the neighbors of V2. And V3, maybe part of it is here, part of it is here, and part of it is here. And I put the parity check matrix of C0 according to the ordering that we discussed before. So I get the parity check matrix for this code. Okay, so it's a definition. Now, what I want to claim is that the distance of this code is large. So for every.
So can you remember what a parity check matrix is?
Thanks, yeah. So I just defined what it is. It's just a matrix of zeros and ones whose kernel is your subspace. So it's just a matrix such that when you take any code word and you multiply by this matrix, you're supposed to get 0. It checks that you are in the code. And the checks are parities because we're working in 0, 1. So it's like a bunch of parity checks. Yeah, sorry for using this terminology. Okay, so the claim here is that for every string that is in the kernel of this matrix, or for every f that is in this code, C, G, C0, that is not 0. So for every non-zero code word, the weight, the number of non-zeros of this function, so it's a function on the edges. So the number of non-zeros is going to be delta times delta minus lambda times E. I mean, this is a string with E coordinates, and at least this many coordinates must be non-zero.
So bigger than.
Bigger than. Thanks. So why is this true? So just let's look at the picture and think of only the edges that have 1. So you have some non-zero function. So there's at least a few edges that are 1s. And color and put, let T be a set of all vertices such that V is incident on some non-zero edge. Okay, so there is some coordinate of f that is non-zero that touches this vertex. I'll put this vertex inside T. Okay, so this vertex inside T, this one, and so on. Maybe this one now. So I have some set of vertices, and what do I know about these vertices? If a vertex touches some non-zero edge, then it means that the edges around it must be a non-zero code word of C0. So there must be at least delta fraction of non-zero edges around it. So it exactly means that this set T has average degree at least delta. Actually here, in every vertex, it's at least delta. It's not only an average. And this means that this set T has size at least delta minus lambda times V. So many vertices are in this set T. And now, whenever you have a vertex inside T, then many of its edges, at least delta, are in E, so you get this expression. Okay, so this kind of shows how this spectral. So what do we see actually from this application? We see interesting, I think, very nice combination of using arguments about spectrum, which are like from the reals, and they don't have anything to do with this F2, combined with parity check matrix or this kind of linear algebra over F2 definition of a code and some combinatorial property of the code. So you see how the spectral and the Boolean algebra somehow mix nicely. Okay, so that was the.
But it can just say, do you know if it's not empty?
Okay. That's a very good question. I mean, I defined this code by saying it's all vectors that satisfy a bunch of linear constraints. So how do I know if it's empty or not empty? One way to do it is to count dimensions. If you have less constraints than degrees of freedom, it's not empty. And so what do you need to do? Just look at the dimensions. You have here E degrees of freedom. And if you choose your C naught so that the number of constraints here is less than half times D, then you'll get here less than V times D over 2, less than that number of rows. And you have here exactly V times D over 2 columns, so you'll have a non-empty code. Actually, it's one of the questions that I think about a lot lately is how to get such a construction and to use some other properties. For example, building the code so that it talks with the graph in a nice way, in a way that you can take kind of more constraints here, you'll get, better properties for this guy, like maybe higher distance, and still have a non-empty code. So kind of finding arguments for getting non-empty codes beyond constraint count. Okay.
Can you also comment what is the purpose of this construction? So you start with a small code on F2 to the D, and now you've created a code on a larger dimensional space.
Oh, great, thanks. Okay, so what is the purpose? So, I mean, people care a lot about constructing codes, and they also care a lot about different properties of codes, like can you decode, given a noisy code word, can you reconstruct the original code? Now, a random matrix will give you a very good code, but you don't know how to decode it. Whereas in this construction, we do know how to decode. I'm not going to talk about it. So that's one thing you get here.
Because you're saying this is a sparse, it's a way of forming a sparse code. Is that how we should think about it?
I mean, if you choose you choose a random parity check matrix that's sparse and you choose it randomly, it will also give you a code with high distance.
Right.
But we don't know how to decode it. It's conjectured to be hard.
So this
No, it's not conjectured to be hard, but no. What I said now is just wrong. No, actually, that will also work. What I just said now will also work. If you take a sparse parity check matrix, you can also decode it. But this is like an explicit construction. One more thing that I want to say is that it also is a local to global construction. You have some property of small code, distance, and it lifts to a property of the big code. And earlier, like, I don't know how many weeks ago, we heard Shashank speak about other kinds of properties that you can take from the small code and lift it to the large code. For example, there is something you can think about, which is like optimal list decoding up to some kind of bounds, like the singleton bound. And if you have it in the small code, you can have it in the large code. So, such things. Yeah.
The claim about the distance type?
I think so. Yeah, I think so. So is the claim about the distance type. So one example you can think about is what happens if the graph is not a sparse expander, but actually a clique. It's still going to be a lambda expander, actually with lambda equals 0. And then the code you have really is a tensor code. How to see it? The best way to see it is actually if the graph is bipartite. So suppose that you think of a graph that's bipartite, it has n vertices on each side, and it's a complete bipartite graph. Okay, and then you have n squared edges exactly, and if you put the same code here on every vertex, one way to think of these code words is as if they are n by n matrices. This is a code word, not a parity check matrix. So the code words here are going to be n by n matrices such that the columns, every column here corresponds to one of these, the neighbors of a vertex. So every column is in some base code C naught, and also every row corresponds to the edges touching this vertex. So you get really a tensor code, and here we know that the distance of a tensor code is obtained by taking a minimal weight code word here and a minimal weight code word here and just taking their product. So it's exactly delta squared. So if you know this, then this makes sense that this is exactly correct. And if you don't know this, then it's not so important. But is there a question? Maybe a comment to say here about the tensor codes is kind of an aside. If you look at the bipartite graph, so you have n squared edges, and I drew them in this matrix this way. But now if I just take one of the vertices and just kind of arbitrarily change the ordering on which I ordered them, it will embed the coordinates of the code in a different way in this table. And there's only one embedding that is good and gives me a tensor code, and the other ones give me something else. And that something else will have smaller rate. So there's something kind of nice and magical in tensor codes, which is that even if the local rate of the code at every location is it's much smaller than half, maybe it's 0.1 or any epsilon you want, you'll still get rate here that's epsilon squared. It's kind of easy to prove. But it means that something non-trivial is happening here, because when you count constraint, there's many more constraints here than degrees of freedom. So there is some kind of redundancy on the constraints here, and this gives me kind of a higher rate than I expect when I count constraints. And maybe, one of the directions to get such things in expander graphs is to be able to imitate this somehow. I mean, we have some constructions like this, but we don't understand the picture, I would say. Okay, so this is background on the expanders and codes, and now let's talk about high-dimensional expanders. So I'm going to talk about simplicial complexes. So really, these are just like graphs. There's one that we like. Yes. Yeah. So this is a simplicial complex with 6 vertices. Okay, so this is the same vertex, 2 and 2. And all the triangles that you see are actual triangles. So this is an example of a simplicial complex. And so we have here vertices, edges, and triangles. And just like we looked at a graph and we were able to define out of it some kind of linear map, when you look at a simplicial complex, you don't only have one linear map, you actually have a chain of linear maps. So I'm going to start by defining the coboundary and boundary maps, but let me just make sure I Okay, so before I define the maps, I just want to say that just like in a graph, we can think of a random walk where you start from a vertex, you go to a neighbor, then you go to another neighbor, and so on. In a simplicial complex, we also have higher dimensional random walks. So for example, you can start from an edge, choose one of the triangles that touch it uniformly at random. So for example, this edge, 2, 3, it touches the triangle 2, 3, 6, but it also touches the triangle 2, 3, 5. So it touches 2 triangles. And I move to one of them. So suppose I move to this one, and then maybe I move to another edge inside this triangle. So I can go back to the same edge, or I can go to one of these other ones. And I can keep going. So that's like an edge to triangle to edge random walk. I can also go from triangle to triangle through an edge, and so on. And in general, I don't like drawing them so much, but you don't really need to stop at 2. You can have a higher dimensional face. In general, one way to think about it is just abstractly. You have a hypergraph with largest hyperedges of size, D faces, they have D+1 vertices, and you close it down. So whenever you have a hyperedge, you also put in all the smaller edges and triangles inside. Okay. So it's very natural to study random walks, and we also care a lot about, I'm not going to write it right now, about the link. So suppose you look at a vertex, you can look at all the faces touching that vertex, and you can see here that this induces a smaller part of the complex, that if you remove this vertex, what you are left with is a cycle of length 5. You can see that in this specific simplicial complex, all the links are cycles of length 5. Right, for example, this vertex 1 is a neighbor of 2, 4, 3, and also of 5 and 6. And I think you get a cycle mistake. Okay, so now I want to talk about the linear algebra part, or the, I don't know, over some group like F2 way of thinking about this complex. So really what we are doing is we look at the collection, let's say, you do it like this. You put the vertices here, you put the edges here, and you put the triangles here. And now I'm thinking of this kind of multipartite graph, and I put a vertex here for every edge, and I put a vertex here for every triangle, and I'll draw an edge if this vertex is contained in this edge. I draw an edge here if this edge is contained in this triangle. So for example, this triangle can be UVW, and so it connects to 3 edges, UV, VW, and UW, and then here I will have UV and W. Yes. You see this structure. So I can keep going like this. And now when I talked about the random walk before, like starting from a triangle, going down to an edge, going back up to another triangle, you can think about this in this bipartite way. But you can also think of this bipartite graph as describing a linear function over F2. you can put some, so you can think of the space F2 to the X1 and the space F2 to the X2, to the X2. And you can think of a linear map that goes this way, so that the value here will be just the sum over F2 of the values in these three places. Okay, and this is what we call the co-boundary map. These are two different maps. We use the same letter delta. Formally, this should be, I don't know, this should be delta 1. I'm not going to care about it so much. So whenever I have a graph that also has triangles, it's not only that I have one co-boundary map, I have several of them. And there's one thing that is important here, and this is that delta composed with delta is 0. So this means that if I start from here, I have some function here. Basically, what is a function in x0? It's just ones and zeros. It's like a set of vertices. The ones are the vertices in the set, the zeros are outside of the set. And I take this delta map, and what do I get here? For every edge that sees vertices from two different types of a 0 vertex and a 1 vertex, I get a 1. And for every edge that sees two vertices of the same type, I get a 0. So really, when I start with a set of vertices and I apply the co-boundary map, what I get here is a cut. Maybe I should draw this. Just, delta. So if F is just an indicator of some set, okay, then delta F is the indicator of the cut between S and S1. Okay, so you should understand here that now I'm thinking of functions that are not real valued, they're just valued in F2. So it's either 1 or 0. Okay, and this should be clear. If I have my graph here and I have some set S, then for every edge that crosses between S and outside of S, delta of F on this edge is the sum of the F on these two locations, right? So delta F on UV is F at U plus F at V. Okay, so it means that it's 1 if U in S and V not in S, or in U, S and V in S, and 0 outwards. So clearly, if I have an edge like this, then delta F would be 0. And maybe before I prove this, maybe I should write a definition of delta more generally. So delta is an operator that takes me from define it. So let me just say, yeah, let me define these things. We denote by Ci of X, and here it will be with coefficients in F2. It's the space of all functions from Xi to F2. So previously I just wrote it as F2 to the Xi. So here I wrote F2 to the X1. This is, I can write it as C1 X F2. It's the same thing. And then delta, this boundary operator takes me from Ci to Ci plus 1. And the way it's defined is that if you give me a function in Ci, delta F at some simplex is the summation of F at all the simplexes below it. Okay, so I'm summing over all the subsets of S of size 1 less. And that's how I get it. And of course, this is in F2. Okay, so I'm just kind of writing out the definition that I drew up there as a bipartite thing. And then if I want to check that delta is 0, I can just check it, but just to understand what it means. So if I have some function f, what does delta of f mean? So at a point p, it's the summation over all s that is, let me write this, less than p, so it's a subset of p, but of size just exactly 1 below. Okay, so of delta f at s. And what is this? If I open up this delta again, so summation x, delta f is summation r less than s of fr. Just using this definition twice. And now what do I see? I see that if I have some simplex p, and then I look at all the possible ways to get to a simplex r that is twice below it, s is once below it. So there is this, okay. Maybe best to think of an example where P is a triangle. Okay, so if P is a triangle, then I'm summing over all possible simplices 1 below, so it's over these 3 edges. So S is either UV, VW, or UW. It's exactly like in that picture over there. And then R is one of the vertices, U, V, or W. U, V, or W. And so what's going on here is that for every vertex, it appears twice in the sum. One's coming from this edge and one's coming from that edge. And since we're over F2, you get 0 always. But it doesn't even matter what F was, you always are going to get 0. And what this gives me is some interesting sequence of maps like we drew up there, so that no matter where you start, after you apply delta f once, you get to some structure that the second delta will always zero out. So the second delta somehow detects linear relations among the first delta. I don't know. We'll see how to think about it. Yes. Okay. So I think. Okay, so maybe let's look at a geometric or combinatorial interpretation of these delta functions on this specific simplicial complex, sorry. We saw that if you start with a set of vertices, meaning you start with some function in C0, okay, then when you apply delta, what you get is a cut. Basically, you get all the edges that cross between that set and the complement. But in this picture, I can also look at this set of edges. This set of edges, let's see if it's a cut in a minute, but what it does satisfy is that delta of this set, so if I think of this is an element in C1, and I apply delta to it, it means that for every triangle, I sum the 3 edges and I want to see what I got. So this triangle sums to 0, this triangle sums to 0 just because it has 2 edges, this triangle sums to 0. You can see that actually this set of edges, all the triangles sum to 0. Okay, so this is a collection of edges that is in the kernel of this delta. Okay, it belongs to the kernel of this delta, of delta 1. But it is not in the image of this delta. So the fact that delta delta is 0 means that everything that came from here will be zeroed here. But it's not that there sometimes could be other functions on other sets of edges that zero the second delta without coming from below. Okay, and this is an example of that. So it's not that I can tell you how to think about it. Sometimes, I mean, the origin of this, of course, came from a manifold where you think of these as certain kinds of holes, and maybe this is the joint. But for us, it will just be some linear space that sits between these two spaces. Okay. Maybe I should also give this definition. Here, we say that B1 is the image, BI. BI is the image of delta I. The ZI is the kernel delta I plus 1. So these are the guys that get 0 by the next delta, and these are the guys that come from the previous, and delta delta equals 0 means that ZI always contains BI. These are called the cocycles, and these are called the cobundles. Okay. So far, what do I have? I have some geometric structure, some simplicial complex, and I can use it to define a chain of linear maps, like here. So I'm focusing on these two levels. And so far, it seems kind of unrelated to codes and to computation. So let me tell you why I would care about this, and what's the connection between this and other areas, connection to computation and to robustness. Okay, so maybe I should have copied this somewhere. Okay, let me actually copy this here. All right. See, this set of functions from xi to f. Delta takes me from ci to c1. And I also wanted to define BI, it's the image. Yes, I should actually define it like this. The I stands for the dimension where you are, so it's the image of delta I minus 1. And ZI is going to be the kernel of delta I. Sorry, so not like I wrote it here. So this is minus 1. So I want to say about the connection to computation. And also I want to talk, kind of leading into talking about robustness. Okay. So sometimes you can look at a sequence of equations, or maybe this is an example I was drawing in the math conversations. Okay. So imagine you have a bank statement where the transactions are x1, x2, x3, and here you have like the balance, s1, s2, s3. all the way down x n plus s n minus 1 equals s n. So this is like your current balance. Whenever you see a bank statement like that, implicitly there is this set of equations that explain to you how the bank reached this final balance. And you're computing this, and maybe you want to check that the bank is telling you the correct thing. And in these applications to Bitcoin and so on, you're not going to read the entire balance of the world, so you want to check it quickly. So this is the kind of computation we do and we are interested in. And you might wonder how to think about this computation. So it turns out that sometimes you can draw it in a geometric way. So you can think of, I guess, a kind of a picture of this equation where this is, I guess, x1, s1, wait, this is x1. So 0 plus x1 is s1, s1 plus x2 is s2, s2 plus x3 is s3, and so on all the way down to s. Right, so maybe I can put a variable on every edge, and I think of every triangle as representing the fact that this sum should be 0. Okay, I have to say that I'm doing everything over F2. Maybe that doesn't correspond to a very interesting bank statement. But you can think of it over, I don't know, the integers. Okay, so basically, this gives me a geometric way of envisioning these system of equations. And when you look at it this way, you also see that this is a very linear kind of system. And in particular, kind of, if you insert one bug in some random location here, and maybe just do the addition wrong here in some random location, it will affect everything, right? So you can see how non-robust this is. Like someone can just do some one error, and after this error, all the equations will be correct. And before this error, all the equations will be correct. Only one incorrect equation, and this will completely affect the bottom line. Okay, so I think that sometimes trying to look at systems of equations and understanding what they are from a geometric perspective can give us a different way to understand them. And this is what's starting to go on here. So maybe it already suggests that maybe you should enlarge this into a plane and maybe triangulate this plane more and kind of have all kinds of partial sums, and this will maybe make this computation more robust. So you can see how kind of understanding a certain computation in a geometric way might lead to some other properties of this computation. In particular, okay, I want to talk about robustness. Okay, so what is the robustness of a sequence of equations? If I have some solution, so imagine, now don't think of this specific system of equations, think of you have some system of equations, okay? Suppose someone gives you a solution and all the equations are satisfied, it's perfect. And now some errors have been introduced, so maybe some of the variables, the values have been flipped. If the errors were introduced at random, this will affect, and if every variable occurs in a constant number of equations, this will affect only a constant fraction of the equation. So if some random errors occurred, some constant fraction of the equations will be affected, but most of them will still be true. Now we ask the converse. What happens if you are told that almost all the equations are satisfied, only a constant fraction are violated? Can you be sure that this comes from a solution that was perfect and maybe some errors have been introduced? So we kind of, if errors have been introduced, we know it affects the solution in a nice way. We want to know if the opposite direction is true. If you have an almost solution, does it mean, if you have something that almost satisfies all the equations, does it mean that it's close to being a solution? So this is the question of robustness. And as you can see from this example, it's not always the case. if I have here a solution where all these are satisfied, one point is violated, and all these are now wrong, almost all the equations are satisfied, but to make it into a solution that satisfies all the equations, I need to change half of the bits. So it's very non-robust. Okay, let's look at another example. Suppose I have variables x1 to xn, and now I put an equation xi equals xj for some collection of pairs ij, which you can think of it as edges in a graph. So if the graph is connected, suppose this is the graph. This is x1, x2, all the way to xn. If the graph is connected, then the only valid solutions here are the constants. Either you put everything 0 or you put everything 1. But this is quite non-robust, again, for the same reason as before. If I just violate one edge, so I just, I'm going to violate this one. And I can then put zeros everywhere here. Zeros on the vertices. And then I put a 1 here and 1's all the way here. Okay, so only one equation was violated, but my string is very far from the set of perfect solutions, which is the all zero string and the all one string. Okay, so this is a very non-robust system of equations. But if I make this graph an expander graph, suddenly it becomes quite robust, right? So if my graph didn't look like this, but rather, it looked like an expander, then no matter how I partition my sets into zeros and ones, there would be many, many, many edges crossing between them. That's the definition of being an expander. Okay, so now I want to, this leads me to the definition of a cosystolic expander. In a cosystolic expander, we have two spaces, so Ci and Ci plus 1. So it's true, I wrote Ci because I'm thinking of those spaces that we defined before. But really, you can also think of just two spaces, U and V, two linear spaces. And here I'm looking at the coboundary map, but really you can think of any linear map. So it's going to be completely equivalent. And now I'm thinking of the set kernel of delta. Okay, so we denote it as Di. But for me, for any linear map, there is a set of solutions that it defines. So if I have a linear map, this is like a bunch of linear equations, really, right? And kernel are exactly those assignments to the variables or those points in U that map to 0. Okay, so it's like the same. Okay, but let me continue the definition here. I look at Ker delta and I ask myself, what does it mean for a function to be in Ker delta? So f is in Ker delta if for every s in xi plus 1, delta f at s equals 0. That's exactly what it means. It means that delta f is 0 everywhere. In particular, it's 0 on every point, on every s. So it means, what does delta f at s being 0 means? It means summation of fr is 0 for all r less than s. So, if we think of f as like a set of edges, so I'm thinking of I equals 1. If I think of f as a set of edges, then delta f is now on the triangles. And really, I'm checking if for every triangle, the sum of f along the 3 edges of the triangles is 0. Okay, so I'm basically, to be in the kernel, I need to satisfy some equation on the triangles for every single triangle. So I can think of it as a system of equations just like this. For every triangle, I need to satisfy that this plus this is 0. And also here, for all the triangles. Okay, so this is kind of one instantiation of what it means to be in Ker delta. Now, what does it mean to be robust? To be robust means, I'm not telling you that f is actually in KL delta. I'm telling you that on almost all the points S, I have this delta f of S equals 0. Not always, but almost always. And I'm asking, does this mean that f is close, meaning you can change just a few of the edges to make it perfectly in KL delta? Okay, so that's the definition. Let me now write it formally. So I'm going to say that I have X is a cosystolic expander with some parameter epsilon I, if it's in the ith dimension. If for every f in Ci, but I'm actually not going to allow a perfect set. So Zi is those f's that satisfy all the equations. I'm looking at something that doesn't satisfy all the equations, so maybe if it's a few. And then I want to say that the weight of delta f, so delta f, it's not 0, but maybe it has small weight. So the fraction of elements of xi where delta f is non-zero, this is what I define to be the weight. And I divide this by the distance of f to the I. So I want to compare how many elements I need to change at f to make it into a perfect solution. And I want to compare it to how many of the equations are being violated. And I want that this is bigger than epsilon I, that's equal. This is my definition. So, okay, now we can take a break, but let me first just kind of interpret this again. So I want to say that I have this linear map delta taking me from Ci to Ci plus 1. Okay? And I'm looking at really kind of the good elements are those that are in Zi. These are the guys that just go to 0. All the equations get 0. Okay, but now I'm looking at the elements f that are not in Zi, but maybe they have small delta f. Okay, and I want to show that if they have small delta f, then if you take this distance to this side and you move epsilon to this side, you get that the distance of those f's from a perfect solution is upper bounded by how many equations are violated, and there is this connection constant. Okay, so it's relating how many equations are violated to how far you are from a good solution. Like in this kind of in this example, we actually wanted that but didn't have it. You have a lot of equations, only one is violated, but you're very far from a good solution. In a robust system, this will not happen. If you're close to being a good solution, meaning you violate only few of the equations, you must also be close. You can find a good solution that's close in having distance to your f. So this is the definition.
You want it for every I or it's
Yeah, so right, so for every I, definitely.
why not epsilon? It's like it's important. It's constant. Like why epsilon I is?
It's not important at all. I just defined it here at level I. You can. It's not so. I'm going to now talk a lot about this definition when I is 1, kind of when the function is on the edges. basically what I want to say is that for expander graphs over here, we saw that every expander graph is a zero cosystolic, meaning cosystolic expansion at level I equals 0, because you see that whenever you have a function, okay, maybe let me just say that. Okay, before we go on a break.
This definition, it really kind of looks like a spectral gap inequality, except you're over F2 rather than doing over C, where we usually do spectral.
Right. Because
It's like
you would measure this as like some kind of norm of delta is like an operator, and you basically measure the norm of this operator, and you divide by what? So here it's not a norm. It's like your distance to some linear space.
That's what you did there too, by taking it orthogonal, right? By taking the expectation to be 0. You actually really took the distance to the linear space found by the
non-zeros.
Right, here you're doing the same thing. Yes, exactly.
I guess if you say you will, your functions are not allowed to be in this space, and then you measure, you need
It has
to
to be
measure.
the kernel, it's the kernel of delta, right? So the norm of delta F must be lower bounded by a constant times the distance of F from the kernel of delta.
Right.
That's a spectral gap inequality, but it's in F2, which.
But it's in F2, and it generalizes to other abelian group coefficients having nothing to do with like measuring and norms. So that's why we have this kind of mixed thing where we measure distance and weight in Hamming distance. But to prove these things, we will use spectral inequalities. Okay, maybe I just say, instantiate this with I equals 0. So when I equals 0, what is Z0? It's all those functions on the vertices that when you take their delta, you get 0. Okay, so it means it's 0. If I have my graph, think of that picture. It's a function on the vertices, so that for every edge, when I add the function on both endpoints, I get 0. So if the graph is connected, the only possible functions are the constant functions. And then let's assume for a minute that the graph is connected. And then when I have a spectral expansion, it means exactly that if my function is somewhat far from the constant, so this is the constant functions in that case, my function is a little bit far from the constants, it means it has some ones and some zeros. And what this inequality is that the fraction of edges, this is exactly the places where delta is non-zero. The fraction of edges is proportional to some constant times the imbalance of the cut. So it's basically here you have something like the size of the cut, and here you have the imbalance of the cut. If you really want to write it, you get exactly the number of edges from S to S bar, and here you get the minimum between the cardinality of S and the cardinality of this bar. This is exactly going to be bigger than epsilon 0. Instead of writing delta F, I write the number of edges crossing the cut, and instead of writing the distance of F to all ones or to all zeros, it's exactly the size of the set or the size of the cut. So cosystolic expansion for I equals 0 is exactly edge expansion. And then for larger I, it's something weird that see how it relates to local testability and to stability of covers. And I want to show a theorem that shows how if you have a simplicial complex and you know some property on each link of a vertex, this property would be local cosystolic expansion or coboundary expansion, then it kind of globalizes to global cosystolic expansion. So we have here a local to global theorem, just like we have in the spectral case, but here it's more, it's a bit harder to prove, I guess. It's more subtle. Okay, let's take a few minutes break. Okay, so few things from the break. I defined cosystolic expanders. What are coboundary expanders? Yeah, so sometimes BI equals ZI, right? Sometimes we always have the BI is contained in ZI. That's the content of what we proved that delta delta equals 0. So BI is always contained in ZI, and sometimes the only things that get zeroed by the second delta map are those that come from the first delta map. And in this case, systolic expander is a coboundary expander because I can replace ZI in the denominator by BI. And but what I get is this kind of inequality for the coboundaries. This is just like a property testing statement. It says being a cosystolic expander or a coboundary expander is just saying that this linear space BI or ZI is a property that is locally testable, and delta is a good tester for it. This is what this statement says. So Peter was asking me, so don't you get locally testable codes from this? I mean, if ZI was a good error correcting code, then what I would get here is that delta, is computing delta on an element that pretends, so there is some element F. It says, look, I'm a code word in your code. I want to test whether F is saying the truth or not. I compute delta and I test it on some random face. Being a cosystolic expander says that this test is good, meaning the fraction of violations corresponds to the fraction, the distance of F from the code. Now, so why don't we get automatically locally testable codes from simplicial complexes that have cosystolic expansion? The answer is that these spaces ZI and BI, they're not good codes. They themselves don't necessarily have good distance. But I want to, so since I didn't, I guess I spoke too slowly, I'm not going to have time to do everything I wanted, but let me skip a few things and move to say how expander codes can be viewed as a ZI in some specific chain. Okay, so I want to say that expander codes as code cycle spaces. Okay. Basically, I want to describe the expander code as a Z0 of some chain delta. Okay. So instead of looking at, so we first, earlier we defined C0X as the collection of functions from X0 to F2. But there's a more general way to define these chains, which allow me not to put a bit on every vertex or a bit on every edge. I'm allowed to put a larger set of coefficients. So this F, and call it a sheaf, it just gives me a space of coefficients for every geometrical object. So, maybe for us, FV would be a copy of C0. So remember, I had this, notation is getting mixed. Here, with the 0 downstairs, it's this little code that we fixed. Okay. So I'm going to take for every vertex, I'm going to have a linear space F sub V, which is a copy of the code C0. And for every edge, I'm going to just put a linear subspace, which is one-dimensional, just a copy of F2. Okay, so how does it look like? It's for every vertex, I'm thinking of like I have a little string of bits attached to it. And for every edge, I have one bit attached to it. So now an element in C0X with this specific sheaf is an element that gives me for every vertex a little code word. No restrictions, just for every vertex a little code word. And what is something in C1 of X and F? It's something that gives me for every edge a bit. Okay, so this is just nonsense, but now I can define a delta map going this way from 0 to 1. And my delta map, well, you can imagine what it is. It's the restriction. So okay, so delta takes an element here. What is an element here? It's a collection of strings, one per vertex, and outputs an element here, which is a collection of 1 bit per edge. Okay, so if I have f in C0, then delta f in C1 over here is, I should evaluate it at an edge and tell you what the value is here. So at an edge UV, what I'm going to take is f of u. It should be something like f of u plus f of v, right? That's what it used to be when everything was bits. But now I can't, how do I take these two things and get something here? So there is also something called a restriction map, which moves from a vertex to a simplex above it, so to an edge, and tells me how to convert this guy into this thing. And the way I do it is by restriction. So the restriction map from this vertex to this edge is this coordinate, and to that edge, it's this coordinate, and to this edge, it's that coordinate. So there's a restriction map that tells me from this element how I convert it to each one of the edges, and it's clear what I should do. I should just kind of distribute the bits to the correct edge. Right, and here I distribute, so I'm gonna take, I don't know, maybe here it's this coordinate and I distribute it here. Okay, so then I just add, so I'm not gonna write the restriction map, it's just gonna be cumbersome notation. But basically I take these two bits and I add them. Okay, so if these two code words are compatible, they actually say the same thing about this edge, I'm gonna get here a 0. And if they're incompatible, I'm going to get a 1. So now what does it mean for f to be Z0? It means that delta f is 0. Delta f at uv is 0 for all v. All v. For all u, sorry, for all uv. So, okay, so I'm saying, what does it mean for f, which is a collection of small code words, one per vertex, to be a cocycle, meaning to belong to this Z0? It means that when I apply delta, on every edge I get a 0. Everything is compatible. So you have a collection of code words, all of them are compatible. And you can see that even though now formally it's a different object than what we defined before, it's really the same conceptually, like there is an isomorphism between this Z0 and the collection of code words, right? Because if I have any code word over there, which puts the bits on the edges, I kind of, every vertex kind of takes all these bits into a little yellow vector, and this vertex takes its bit to hit the yellow vector, and by the way we defined it, the delta will be 0. Okay, so this is an isomorphic way, and I like to think of it as like the local view way. So instead of putting the bits on the edges, we collect them into little local views, one per vertex, and they have to be, and being in the code means these local views are perfectly compatible. Okay, so expander codes can be described as cocycle spaces. And now you can ask, are they cosystolic? So what is they? Are there graphs such that you have cosystolic expanders? Let me say that are. Okay, in other words, can I construct a code like this that is locally testable? Okay, so that's exactly locally testable code. So it's exactly a collection of, okay, it's this kind of Z0, but with this extra property. So what we need, so these are codes such that for every F that is not in Z0, okay, so collection of local views here, but it's not a perfect code word. I want to know that, is it true that the weight of delta F, this is counting how many inconsistencies do I have? Every time this local view is inconsistent with that local view, I get a 1. So I'm counting how many edges are violated. Okay, is this always bigger than? So let me now not write it in the quotient notation, but I write it epsilon 0 times the distance of F from Z0. I just copied what's going on there. Okay, so is it true that if I have only, say, one violated edge, then there should be roughly like one or a very few number of vertices where I can change F and make it into a perfect code word. Okay, so in general, a locally testable code, we don't usually describe it in this local view way. We describe it as a collection of strings such that you have these parity checks. But you can always kind of convert it to this local view way, just like I did between that board and this board. Let me not do it. So let's kind of maybe believe it and ask ourselves, are expander codes already as they are locally testable? Is it true that if I have here a very good expander, maybe it's a random graph, a random Cayley graph, or whatever, is this collection already locally testable? And okay, the answer is no. If it was yes, then we would have known about this long ago, before all this high-dimensional expansion direction emerged. The thing is, if you remember how we proved distance, we didn't care about the structure of the local code. All we cared is that its minimal distance was delta. So all the strings in this local code had weight at least delta if they were non-zero. That's the only property we use. So imagine a modification of the expander code. Imagine that in one of the vertices, instead of allowing C0, I allow C0 plus one extra vector. I add some string to C0. Just in this vertex. Everywhere else, I don't. Okay. If C0 was kind of small enough, and I add another kind of high weight code word, I get a C0 prime that is slightly larger, but still the minimal distance will be large. Maybe it won't be delta, it will be slightly less, but let's even pretend it's still delta. That's definitely possible. Okay, but now I allowed here slightly more possibilities. It could be that the entire dimension of this entire code increased by 1, because you can think of it as if I removed one constraint. I removed one constraint, maybe the global dimension increased by 1. Okay, it could be that the global dimension didn't increase. So even though I said that I allow here more, de facto this doesn't happen. But if the graph is random and the codes are random, it actually will happen and the global dimension will increase by 1. Okay, so what does it mean the global dimension increased by 1? There is now a new global string that wasn't there before, and it's in the new code. So what does it mean? On every vertex that is not the special one, the local view is in C0. And in this special guy, the local view is in the new C0, so I use the extra degree of freedom that I had here. So if I look at that string from the point of view of the old code, it only violates like this vertex. So, if I force it to be in the old code, maybe a few of the edges will be violated. So it only violates a tiny, tiny fraction, like 1 over the number of edges, or d over the number of edges are violated here. But let's see how far is this new string from the code. So this new string that wasn't in the old code belongs to this new code where here you have C0 prime instead of C0. But the same argument that we did for why the code has distance still holds. If you look at the set, we still have it over there. No. If you look at the set of vertices that touch non-zero edges and it has average degree, at least delta, there's going to be still a large number of vertices. So the same argument that showed that our code previously had large distance is still going to hold, even though we changed the code here. So it means that this new code word that wasn't there before is far from any other code word. In particular, it's far from all the code words that were in the earlier code. So what does it mean? It means that this new code word, to make it into a good code word, I need to change it on a constant fraction, like on many places. I need to change it to make it into the old code, even though it only validates like one constraint. Okay, so it's like the worst nightmare. It's furthest away from locally testable that you can imagine. Okay, so what? How did this happen? The problem was that, okay. One way to see what happened is that once I relaxed even one constraint here, I increased the code. In comparison, when I look at known constructions of locally testable codes, even if you relaxed one constraint, the code doesn't change because there's so much redundancy that these constraints are already kind of expressed as linear combinations of other constraints. And this is what happens in this chain of linear maps. Okay, since when you have a chain of linear maps, it means that there's a lot. The second linear map essentially describes redundancies among the linear constraints of the first linear map. So if I had these redundancies, then this relaxation would lead to nothing. There would be no counter example. Okay, so now I want to even describe a construction of a locally testable code using this chain. So let me just erase this picture. And I'm going to add another part to this chain, and I'm going to have something like this. Okay, so what did I do here? Now I'm thinking, in fact, instead of being on an expander graph where I have vertices and edges, let's assume I also have triangles, okay? Or it doesn't really matter if it's triangles or some other form of higher dimensional faces like hexagons or maybe squares. And I'm going to have a sequence of linear maps. For every vertex, I'm going to have some code. Okay, so now I'm going to change it a little bit. For every vertex, I'm going to have code. I guess I'll call it C0. For every edge, I'm going to have another kind of code, let me call it C1. And for every higher dimensional face, like a triangle or a X2, I'm going to have, not like this. Well, here I'm going to put a bit. Okay, so now I'm going to, so if it's a simplicial complex, then it's going to be like this. For every triangle, I'm going to put a bit, like 0, 1, and so on. And then for every edge, I'm going to put some kind of small code word, like something in C1. And for every vertex, I'm going to build some slightly larger code word, which is in C0. Okay, so I have 3 types of spaces here. The most simple one is just bits on the triangles. Slightly more complicated ones, I have like little code words on the edges. And even more complicated one, I have like bigger code words on the vertices. But even those bigger and even bigger, they're all very local. If my graph is constant degree, then kind of the interpretation of this code word is that it basically tells me a value for every triangle touching this vertex. And the interpretation of this code word is that it's telling me a value for every triangle touching this edge. So it's basically, if you think of it, it's like you have an edge and then all the triangles on it, they form some kind of code word. For another edge, they form another code word. And for a vertex, all the triangles touching it, it's like its link, they also form a code word. And now you have this, this delta map that says, if I have a collection of code words, one per vertex, I can apply delta, and it gives me a collection of code words on the edges. How does it go? Well, for every edge, there's this code word from this vertex and this code word from this vertex, and you basically apply the restriction map. So maybe it's one of the columns of this code word, and then it's like, I guess I'm being a bit more too vague here. And too vague. Okay. Don't want to go over time, and I don't know how much, how I can squeeze this into 10 minutes.
You can go over that.
Okay,
Well, you usually sit.
yes, you are. You're doing a great job. Okay, let me stay at a vague level, and but I'll try to clarify. Okay, so just like before, I described an expander code by saying for every vertex I have a local view, some code word, and I compare two endpoints, two vertices. I basically restrict their code word to the geometric component they have in common, and I just want them to match. So the same thing will happen here. A vertex will assign bits to all of the triangles touching it. And it's not just any assignment to all of the triangles touching it. It only assigns values to these triangles that belong to the code on that vertex. Okay. So, but it does give a value to every triangle touching it. Similarly, this vertex gives a value to every triangle touching it. Now, if these vertices share an edge, it means that they have some common triangles, right? This one, maybe they have many common triangles touching both of them. So the code word from this perspective tells me values on all of these triangles. The code word on this perspective also tells me values on these triangles. And the delta map will just first restrict from all the triangles touching this vertex to just those touching the edge, and then combine them, just add what you got from this vertex and what you got from that vertex. So I guess I erased what I wrote. Yes, I erased it, but it's exactly like we did before. Let me erase this. Let's say that, so again, delta, so if I have F, which is in C0, so it's a code word per vertex, then delta F at some edge UV is like F of U, but there's going to be some restriction from U to the edge UV, and also F of V, but again, there's going to be some restriction from V to UV. So the restriction maps kind of take a bigger element in the coefficient space of a vertex and move it to a smaller element in the coefficient space of an edge, basically from a bigger local code word to a smaller local code word. And this addition, it's addition of, now it's not addition of 2 bits like we had before, it's addition of 2 vectors in C1. So this belongs to C1. This is the C1 with the subscript. Okay, it's just a code. maybe I should have, I don't know, called it some curly C1. Okay, so this is in curly C1. Okay, why is it nice that it's in a code? The reason that it's nice is that a code has either it's a 0 word, or if it's not a 0 word, it has many non-zeros. So what does it mean? That if I have two vertices U and V, and they don't agree, there's a mismatch. This guy, the restriction is something, and this guy, the restriction is something else, and there's a mismatch. Then there's going to be many triangles that see a problem, many triangles that are non-zero. And what does it mean, many triangles that are non-zero? There's going to be many W's here that see this problem. So the local point word of W, it can only agree either with U or, well, I guess, maybe V is here. It can either agree with U or it can agree with V, but it cannot agree with both because they disagree with each other. So you have this kind of propagation that if some pair disagree, then there's many other third guys that also disagree. Okay? And this is kind of similar to how we proved the distance for expander code, where we said if there is some non-zero, then there's many non-zeros, and it kind of propagates. So you kind of propagate forward, and now you want to use the expansion, not of the graph, but of the random walk that goes from maybe from edge to edge through a triangle. Okay. I kind of ran out of time way faster than I expected, but now you kind of resort to the properties of the random walks on this higher dimensional complex to show that if there is some disagreement, then there must be more disagreements and more, and this is going to give you local testability. So let me
Where does the spectral gap of this random walk come?
where does the spectral gap come from?
Random walk on the triangles. Or on the edges that goes through a triangle. You
No.
establish that.
Oh, okay, yeah. It's here when I talked about expander code, I started with a graph that had a spectral gap, and I started with a code that had local distance, and I concluded a global thing.
Yes.
Similarly, I'll start with a two-dimensional complex that has some nice spectral gaps, not only as a graph, but also for higher random walks.
That will be the input. So you assume
That's an
you have a
input.
way of constructing those objects. You
Yeah.
haven't shown us how, right?
No.
Okay. This doesn't follow, for example, from that condition. I kind of lost track of where that condition enters here. This cosystolic, if it doesn't go.
Right. What I'm saying, I gave this definition, and then I said it's really like local testability. And I kind of said, I don't have enough time to talk about both things, so let me just talk about local testability. It's the same definition. Instead of ZI with coefficients in F2, we now have ZI with these more elaborate coefficients, but it's exactly the same definition. And now the point is that here, this definition, it talks about just one delta. If you look at this definition, it doesn't need to have like a chain of linear, one delta. But then when I try to construct this definition to get a locally testable code, okay, I look at my expander codes and I see they fail. And then this is a construction. If you have a chain of linear maps and you have these random walks that mix rapidly enough, and also there's some other local conditions that your local code needs to satisfy. It needs to satisfy not only local distance, but also itself, it needs to be somewhat locally testable. If you have all these things together, then you have a locally testable code. Right, so basically there's two theorems that are analogous. Let me just say them and I won't prove them. Okay, so the first theorem And this was proved by Kaufman, Kashdan, and Lubotsky. And then for higher dimensions by Brian Kaufman. This theorem says that if X is a link expander, so this is just a spectral condition, all the links are spectral expanders and so on, and the link of every vertex is a coboundary expansion, coboundary expander. Okay, so this might look mysterious. This contains some local property. It says for every vertex, I just look at part of my complex that is the link of this vertex, and I get a simplicial complex, which I need to be a coboundary expander in particular. And I want to say, okay, here I'll say it's a one coboundary expander, meaning this complex needs to be three-dimensional. Meaning has 4 dimensions, right? 0, 1, 2, and 3. So the thing is an expander, and the link of every vertex has some local property it satisfies, which is a linear algebraic type of property. Then it is a Cosystolic expander. Then X itself is a Cosystolic expander. Cosystolic. Okay, so this is a local to global theorem. It says if you have Cosystolic expansion in the links of vertices, and they're coboundary expanders because there are no local cocycles, then you have global testability behavior. So basically, if you have local testability, you have global local testability. That's this theorem, and then there's a very analogous theorem for locally testable code. So this is the work with Evra, Livne, Lubotsky, Moses, and also Pantelev and Galachev. Pantelev. They proved that something like that if okay, instead of writing it something like that, if you have a chain map like this, and for every vertex, okay, you have a complex X, it has appropriate spectral expansion, and for every vertex, this code is locally testable itself. That's like analogous to this property. Okay, so if you have some complex, it's chain of 2 maps, and every vertex has some local testability. So let me write it: spectral expansion plus local LTC. Together, you get global LTC. So in some way, this is just kind of taking these ideas and extending them to the world of codes. Here, you don't have error correcting codes because these cocycle spaces don't have distance. So you need to work hard to construct an appropriate complex X, construct appropriate codes to get this thing in. Siki described it a little bit last week. One construction, I guess I should also add that one. There are more constructions by now. But you always need to have some kind of global spectral behavior plus some local linear algebra magic somehow. go together. Yeah, let me stop now and. Okay, if no questions now, you can always ask me at any point.